Thank you very much for the invitation. My name is Valerio Carruba. I'm going to talk about the use of convolutional neural network models applied to the identification of images of asteroid resonant arguments. This is a work that I've been doing in collaboration with people from my research group, Safon Argibai, Gabriel Carità, Rita Domingos, Mariana Oman, Bruno Martins, Laura Lorenzo, and Breson Alves. So for those of you that are not familiar with artificial neural networks, the neural network in biological systems served as a model for artificial neural networks. A typical INN shows a neural network with an input, an hidden layer, and output layer, and they may have several hidden layers in between. They share the same fundamental building blocks, neurons, weights, biases, and active action functions. This part works similarly to the human brain, can be trained using the same techniques as other traditional machine learning techniques. So the most simple deep learning model is the perceptron, which is an algorithm for supervised learning of binary classifiers. A binary classifier is a function we can decide whether or not an input represented by a vector number belongs to some specific class. It can be generalized for multi-class classifications or problems with more than just two classes. So when you are dealing with problem of computer visions, one of the most commonly used tools is the convolutional neural network. This is a type of neural network model originally designed to work with two-dimensional picture data. And this its name derives from the convolutional layer. Convolution is a linear procedure involving the multiplication of two-dimensional array of weights with an input array. So essentially, you multiply this array with a filter and you obtain what is called a feature map, which is a two-dimensional array. So one problem with this approach is that the feature map often captures the precise location of features in the inputs. So every little adjustment will produce a different feature map. Common solution for this issue is to utilize a pooling layer. So a pooling layer builds a new pool feature map with the same amount of features by working separately on each feature map. The pooling layer operation of filter, for instance, is often applied with a stride of 2 pixels. This is typically smaller than the feature map. A common operation used for pooling are the mean or the maximum. So you can see an application in the figure. You can select the blue squares. The maximum value here is 9. So this will map this 4 square into 9. It will do the same for the green square into 7, and so on and so forth. So there are several convolutional neural networks that have been used in the literature. Here I'm going to revise 3 of the most common use, which are the VGG model, Simonian and Zisserman in 2014, aimed at standardizing architecture design for convolutional networks. And this architecture is commonly referred as VGG by the lab name, the Visual Geometry Group at Oxford. They use several small filters becoming a new standard. The most not all convolutional layers are followed by max pooling layers. Many architecture versions were built and assessed, but because of the performances in depth, 2 are the most commonly used, the VGG 16 and the VGG 19. Finally, the VGG study was among the first to make models of weights freely available, and this set a trend among research in the area of computer vision. Then we have the inception model, which was introduced by Sajadi et al. In 2015. This is called because the architecture which was introduced in the model, which is called inception. Inception model is a primary innovation of the inception model. Is a stack of parallel convolutional layers with varying filter sizes, such 1 by 1, 3 by 3, and 5 by 5, as well as a pooling layer with a 3 by 3 maximum, the output of which is subsequently concatenated. We have the residual network model, or ResNet, which was introduced by He et al. In 2015 and is an extremely deep model. The concept of residual blocks that utilize shortcuts connection is crucial to the architecture of the model. These are just connections where the input is transmitted to a deeper layer while remaining unchanged. The residual block is a pattern comprising 2 convolutional layers activated by ReLU, where the output and input of the block are combined. And this is called the shortcut connection. So how do you measure the performance of a CNN model? There are 2 most common used metrics. You have the consentropy loss, which is defined by minus the sum over ti log pi, where ti is the truth label and pi is the probability for the ith class. And the entropy, which is the fraction of the accurate measurement over all the measurements. So you have the true positive plus true negative divided by true positive plus true negative plus false positive and false negative. The entropy should ideally tend to 0, while the accuracy ideally should tend to 1 for best performing models. So one of the most common limitations of deep learning model is their tendency to overfit the training data. Overfitting occurs when the neural network model learns all the minute features of the training test. So you can use a validation set for detecting overfitting. You can see here a case where overfitting is happening. So while the performance for the training set, which is the blue curve, is very good, when you apply the model to a validation set, a separate set, the performance is not so stellar. And that's because essentially we have a problem of overfitting. So you can correct for overfitting by introducing what is called a regularization method. You can have data augmentations, which entail creating duplicative of the training data set with minor random changes. So if you fit the pictures of the cats, you can have a rotation, symmetry within axis, so on and so forth. You can have dropout, so you can radically remove nodes from the network, and this will reduce the performance of the training set, but you also reduce overfitting. And you can finally have a batch normalization, which employs a transformation that keeps the output mean and standard deviation close to 0 and 1, respectively. So what are applications to asteroid families? I'm going to go a bit slower because I assume that not many people may be familiar with these problems. So asteroid family is a group of asteroids that are formed by a collision or a fission event. They can be identified in domains of proper elements, which are constant of the motion over million years. Usually the orbits of asteroids are identified by 6 parameters, the same measure axis, eccentricity, inclination, longitudinal nodes, argument of pericenter, mean anomaly. And these are instantaneously perturbed by planet, but you can create constant of the motion for timescales of up to million years by synthetic methods or by analytical methods. And in these domains of proper elements, asteroid families appear as groups. So you can see here groups of asteroids like the Vesta family, the Coronis families, the Eos families, Maria, etc., which are located in the main belt, which is the place in the solar system where most asteroids are found between the orbit of Mars and Jupiter. So many asteroid families interact with secular resonances. Here you can show the location of some secular resonance in the same major axis sign of inclination domain. So what is a secular resonance? The nu-6 resonance, for instance, is resonance that occurs when there is a commensurability between the precession rate of the pericenter, the longitude pericenter of the asteroids, and the longitude pericenter of one planet, in this case Saturn. So the pericenter is the position in the orbit which is most closest to the Sun. And when you have a perturbation from other planets, this position is not fixed, but may vary with time. So this has a period, which is a period of precession, and the inverse of this period has frequency, which is called the precession frequencies of the pericenter. If the precession frequency of the asteroid close to that of a planet, you have what is called a linear secular resonance. And the nu-6 resonance, which is the G-G6 resonance, is one of the most powerful secular resonances in the main belt. So what does it do? Essentially, objects that are capturing this resonance will have the eccentricity of their orbit very increased by several order of magnitudes. And this means that the orbit becomes more and more elliptical, and this may cause interaction of the asteroid with terrestrial or even Jovian planets. So the common knowledge in dynamics is that the nu-6 will produce instability. But inside the nu-6, you can have stable islands. So you can think of the nu-6 like a very fast river that will deliver asteroid away, except for these stable islands would resist some stable population. So what kind of orbits you can see? You can see here plots of time dependencies of the resonant argument of the resonance, which is var p minus var p6, the longitude presenter of the asters minus the longitude presenter of the planet. You can have several behaviors. You can have oscillations in around 180 or 0 degrees, which are the equilibrium points. So you can have 180 in the first plot A, or 0 in the fourth plot C, the third plot C, sorry. And these are two equilibrium points of the Nu-6 resonance. The first one is called anti-align orbits because for these asteroids, the presenter of the planet and of the asteroids points into opposite direction. And the second is called align orbits because the two presenter essentially points in the same direction in the skies. And then you have objects that are not in resonance. For these objects, the resonant argument will go from 0 to 360 degrees and cover all the possible range of values. So how do you identify this population of asteroids in practice? You can plot, you can analyze the time domain, time behavior of the resonant argument. You can see here an asteroid that is not in resonance, 254 Barbara, asteroid that has phases of oscillation and phases of circulations, an asteroid that is oscillating around 180 degrees, and an asteroid that is oscillating around 0 degrees. So this is fine and good if you have a population, small population of asteroids. But nowadays, we are dealing with a population of several thousand of asteroids, and we expect this number to much increase when we will have data from the Vera Rubin survey starting in 2024. So rather than doing it visually for single asteroids, the goal of our work is to create models of each resonance. So to identify the population of asteroids in Lucin's resonance stable orbit, we use the artificial network model described in Karub et al. 2021. So this is a 5-step process. We integrate the asteroid orbits and the gravitational influence of all planets. We compute the time series of the Nu-6 resonant argument. We obtain images of this time series, like the one that are shown in the figures. And we train the model over this set of training data, so a set of training data, and to classify automatically the kind of figures that you have. So here you have several figures. You have a circulation, a libration around 180 degrees, alternating circulation and libration, and so on and so forth. So this method allows to retrieve 15 asteroids on a line orbit and more than 1,600 asteroids on anti-align orbit. And align orbit are much more rarer than anti-align ones. So once we have this data, we can actually create more advanced deep learning model using the VGG inception ResNet model with and without regularization. And this was trained for sets of asteroids in the Nu-6 resonance and mid-motion resonance with Mars, in a stereo mid-motion resonance with Mars. For the Nu-6 resonance, which is the one that I'm going to discuss in this talk, the VGG plus DA plus DO was the best performing model. It still will be the first plot in the series. We show that the difference between validation and training set are much smaller than the other cases. So we have now a model that can train, we can recognize the images of several thousand asteroids in seconds. And this is a major improvement with respect to what we did in the past, which was visual inspection. We would require weeks or even months of analysis. It was always subject to errors by a single observer. So this is fine and good, but having a set of asteroids, a new set of asteroids should not be a goal for itself. What can we learn from these new sets of resonant asteroids? The inner main belt is the region that is closer to the Earth in the main belt. It's between the 3 to 1 and 9 to 4, 3 to 1 and 4 to 7 mid-motion resonance with Jupiter. And we identified two asteroid families that interact with the Nu-6 resonance. One is the VA family, which was already known. And there is a new family, which is a 12-1988 Tiffany Kepler group, which is a small value of properties and major axes and inclinations, and is shown in the plot. Okay. Sorry. Okay. There was a problem with my presentation. Just one moment. Okay. So we can perform a backward numerical simulation for the new families, and we apply two methods that allow to determine the age of the family with high precision, which are the backward integration method and the close encounter method. So the backward integration method, you integrate the difference of nodal longitude of the nodes of asteroids and the parent body. You can see in the figure that there is a convergence of all the values in a time interval that goes from 3 up to 7 million years. With the close encounter method, you also perform numerical integration in the past, count the number of close encounters that you have between the parent body and a secondary body. And so it's expected at the time of the family formation, this number should have a maximum. So both methods suggest an age of the family which should be of the order of 3 million years plus or minus 1.2. And this is the first ever identify a young asteroid families in the NU6 secular resonance. Also, the Tina family was the first family ever found in stable configurations of the NU6 resonance. And with this work, we identify a series of new objects, which are the empty circles in the plots, which are part of a newly discovered resonant halo for this family. So the halo is a part of the family which is not detectable using standard method for family identifications. And most families have been found to have halo, but this is the first case ever found of a resonant halo in the main belt. Sorry. So to conclude, the main goal of this work was to identify which approach a more modern available CNN model was less prone to overfitting, more efficient in predicting the label of a larger dataset of asteroid resonant images. The regularized evaluation models can predict the label of thousands of asteroids with high accuracy and beta score. This model will provide and sell quite available when the Vera Zero Beam survey will start to discover millions of new asteroids after the beginning of operations in 2015. So thank you so much for your attention. If you are interested in more detail about this work, we have two published papers on multi-notice and celestial mechanics and dynamical astronomy. And you can also check out the MASB Research Group website or send an email to the research group address. Thank you. And I think I can start answering questions.
Thank you very much, Dr.
I will stop
Thank you so much, Doctor, for sharing your, yes, sure, for sharing your priceless expertise and knowledge with us, of course. You really graced our webinar with your presence. Is my voice audible to you? Can I read the questions for you?
Yes. No, I can hear you.
Okay.
I can also read on the chat. So I can read
of
the
course,
question
I can read
if
them
you
to
want.
you too. Okay, sure, that would
Please go.
be great. I really appreciate it.
I think there is a question about does the optimization of artificial neural network models apply to the identification of images of asteroid resonance argument? Well, what it does is that if you apply a model and you just don't validate it, you may actually go into this problem of overfitting. So you may actually think that you're getting great results, but when you use a different set of images, not the one that you use for the training your model, your result actually will not be so good. Yes, what it does essentially makes the model less set dependent. If you apply these methods of regularizations, you can be more confident that what you're actually predicting are like the actual labels and not fictitious one. So ultimately, you will always, what we do in our group, you select the labels with the deep learning model, but it's always extremely recommended that the most interesting asteroids are checked separately by visual inspection. So we have a team that actually does that. I hope that answered the questions.
Thank you so much for answering the questions. We highly appreciate that, and we highly appreciate your time. And thanks for being with us in this webinar.
Thank you, my pleasure. Thank you for inviting me.